We're going to look at a problem about, it's going to say we want the conjugate acid. So if something's asking for the conjugate acid, and whatever, that means whatever you started with had to be a base, right? So what was an acid, what becomes an acid was a base on the other side of the equilibrium arrows. So it really doesn't matter what I put here, but so don't forget your definitions. Conjugate acids, right, are electron, right? Any acid is electron deficient, right? And any base is electron what? Rich. So if I were to give you the conjugate acid, to find what the conjugate base is, you just find the most polar bond to hydrogen. Right? So if I gave you the conjugate base of this and said, or gave you the conjugate acid, let's say, let me erase that quick. If I had this and I told you this is the conjugate acid, and I asked you what's the conjugate base, and asked you how to figure that out, you look at this and say, well, where is this the most acidic at? Where's the bond most polar? What bond is most polar here? OH bond. The OH bond, right? Plus we're talking about acids, right? Just makes sense. The only thing bonded to hydrogen, right? There's still a carbon here, right? Everybody realize that. This is a carbon with 3 hydrogens, right? But CH bonds aren't as polar as an OH bond. Right, so the conjugate acid, or the conjugate, or the base of this, or the conjugate base, that's why I don't like the terms. I mean, it's just, they're equilibrium arrows. The star materials are, it's all arbitrary, what you call the star materials or not. Right, but the base of this would be just with that hydrogen gone. That would be the base. If you did it the other way around, right, I could start off with this as my base and say, well, what's the conjugate acid of that? That's a little more complicated question, but you should be able to figure that out. Where is this most electron rich? Right? Because if it's a base, we need to find out where it's most electron rich to figure out where the H is going to add. Where's the most electron rich? On the where? Not the sulfur. The sulfur, right? Look at your periodic table. An oxygen. Which oxygen? There's a problem. There's an oxygen here and an oxygen here. This is a what hybridization state is this oxygen? sp2. It has 1 pi bond. What's the hybridization state of this oxygen? sp3. Okay, so they're going to have lone pairs, right? Both of them have lone pairs. Which lone pair is more reactive? What molecular orbital is this lone pair right here? What molecular orbital is that lone pair in? It's in sp2. What molecular orbital is this lone pair in? Which one's more reactive? More reactive. Which one's more reactive? Right? sp3 is. So here's an sp2 orbital. Here's an sp3 orbital. Right? The farther you are from the nucleus, the more reactive you are, right? So I would guess that this would be the more reactive site. Right? So it's almost a two-layered problem. You recognize an oxygen is going to be more electron rich. Good. But now you had to choose which oxygen the hydrogen is going to bond to. I would choose this one because these lone pairs are in an sp3 orbital, which is farther from the nucleus, means they're more reactive, more prone to do reactions, right? They're farther from those plus charged protons. So I would guess the conjugate acid of this would be this. So another question about ranking strongest acid, Bronsted acid, the weakest Bronsted acid, so more reactive to least reactive. So of course Bronsted acid, we need to know what that means first before we work on the problem. It's an electron deficient, right? All acids are electron deficient. This is a particular type of Lewis acid that involves H, right? Involves bond to hydrogen. So that's a Bronsted acid. So your options you have here, you have HCH3, you have OH, you have HF, HCl, and NH2. That's it. Okay. So what I like to do with these problems, I always like to try to get it, find the outliers, things on the ends, right? Which one's the most reactive, which one's the least reactive. Which one of these has the least polar covalent bond? If you're not sure, right? So what's the other way to look at this is, well, what do they all have in common? What's the unifying factor here? Hydrogen, right? Hydrogen, 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 hydrogen. Okay, good. What's different? Carbon, oxygen, fluorine, chlorine, and nitrogen. So what I like to do is I look at the periodic table and say, how are these related to each other on the periodic table? What's the relationship on the periodic table? And you should remember one of our things we talked about, acidity, one of the big factors is electronegativity, right? And then, right, so as you go from left to right across the periodic table, what happens? Electronegativity increases. So if you're bonded to a more electronegative atom, that bond is going to be that much more polar. So which one of these bonds is the least polar? HCH3, right? Carbon-hydrogen bond. That's not a reactive bond, right? So this would be, I'm going to say this is 5, the weakest, least reactive acid. All right, that's 5. What's the most reactive acid?
That's what.
So wait, this is a Gen Chem question. You should know this already. What are the strong acids? Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, chloric acid, and perchloric acid. You should just be all, there's only one strong acid in the bunch. Right? We can talk about why that is in a second, but you should have automatically recognized, right? Maybe you didn't, but HCl, right, is the most reactive acid because you know it's a strong acid. Now, why it's more reactive than HF, we'll get to in a second. So what's the next most reactive acid? What's number 2? HF, right? That's right according to electronegativity rules, right? That's the one that's most electronegative and a polar bond to hydrogen. But is electronegativity the only factor that matters for acidity? Right, we had 5 of them, right? We had electronegativity, we had induction, we had resonance, right? The delocalization, we had size, and also hybridization. Right? So part of this question was, so you wouldn't necessarily know one part, but you should have known part. I'll get to it. So what's next? So now we have water, we have HO and HN. Where do they lie in this whole deal? So which one's more reactive? Water, HO or HN? HO should be, right? Because that's a more polar bond. And then HN fits in there. Now you could have looked up the pKa's and got this answer, right? It would have been easy. So one of the hard parts here was, well, we're comparing 2 factors, right? What are the 2 factors? What are the 2 factors we were comparing here that affect acidity? We were comparing 2 things. What were they? Electronegativity and size, right? Now I told you, right, I wouldn't make you compare apples to oranges. It's not fair, right? It's hard. But, right, you should recognize HCl as the only strong acid, just cuz. But why is HCl a stronger acid than HF? What's going on with HCl and HF? Cl is bigger, so there's less orbital overlap. You can draw that picture, right? There's Cl, right? Less orbital overlap, more reactive bond, not as much, right? Not a very strong bond. Also, you could think about the conjugate base, right? Cl minus is going to be more stable because it's bigger. It can spread those electrons out, right? That's not resonance, but it's still stabilization, right? For a reaction to take place, one of 2 things. You either have reactive starting materials and or stable products. You can't have both always. You need to have at least one for a reaction to take place. Okay, another conjugate acid, conjugate base question. So it's written like this. So this would be a double take. We can get a couple things out of this. right? This is this, and they're saying this is your acid, and they want to know what the conjugate base is. So the first part of this problem, I'm going to argue you need to be able to know how to do this expanded structure. Or you got to actually draw this out. And actually they make you draw it out. That's part of the deal. All right, so what does this look like in an expanded form? It's C double bond O. There's an H there, and plus charge. One lone pair. And then when it's bracketed like this, parentheses, there's two. That means this carbon, right, is bonded to two CH3s. So don't forget your rules, right? How many bonds does carbon have? Have to have. Has to have 4, right? So here's the carbon bonded to this oxygen, sigma and pi, and then 2 sigmas to 2 other carbons sitting out here. All right? So that's one part of the problem. The next part of the problem is you got to figure out what does the conjugate base look like. So this is the acid. So you find the most polar bond to hydrogen. Where's the most polar bond to hydrogen at? The OH, right? I'm going to take it a step further, and I'm going to say I have OH minus in there. Might as well bring some mechanism problems into this, right? I'm going to use these electrons to take that H. The 2 electrons in this bond are going to the oxygen. All right, equilibrium arrows. Nothing changes here. Notice how that one lone pair, this lone pair right here, the oxygen got it back, right? The oxygen got those electrons back. And the other product we made is water. Now, what do we need to check before we get done? Right? Do we balance our charges? But there are charges over here. It's all about the net charge. Overall, plus 1 minus 1, that equals 0. So as long as the net charge stays the same, right? So be careful about that. So in this case, the conjugate base is just this ketone, carbonyl. All right. So be able to go back and forth between those terms is important. All right, so let's do a problem where we're discussing Lewis acids versus Bronsted acids. So one way to think about this, or just Lewis anything. So here's Lewis, let's say acids. That's the big umbrella, right? And underneath the big umbrella exists Bronsted acids. Right? What that means is all Bronsted acids are Lewis acids, but all Lewis acids are not Bronsted acids. Right? Lewis acids are areas of electron, right? Just acids in general. What's an acid? Acids in general are electron deficient. A Bronsted acid is electron deficient, but specifically at what element? At a hydrogen, right? So it's electron deficient at H, right? This is its electron deficient. It doesn't matter what element it is, right? A Lewis acid can be any element that's electron deficient. A Bronsted acid is only electron deficient H's, right? A Lewis acid can be anything, right? Of which hydrogen is one thing. So all Lewis acids are not Bronsted acids, but all Bronsted acids are Lewis acids. So what does this mean? So one example they show, they say, okay, here's OH minus plus HBr, and they're telling you it goes to this and Br minus. Great. They want to identify what the starting materials are. What are they? So this is obviously a base. It's electron rich, right? The question is, what kind of base is it? So we know for sure it's one kind of base. If it's a base, it has to be a Lewis base, right? All bases are Lewis bases, right? So it's Lewis for sure. Is it a Bronsted base? So a Bronsted base refers to specific types of bases that go for what? That grab what? React with what? H's, right? Is this one reacting with an H? Yeah, so it's also a Bronsted base. This is the acid then. It's for sure a Lewis acid. It's electron deficient, right? Is it a Bronsted acid too? Is it the one that is does it have an electron deficient hydrogen? Yeah. So it's a Bronsted acid too. Let's also draw the mechanism out. Draw our lone pairs in. All right, there's that new set of lone pairs it got. Right, it already had. Right. Where do electron arrows begin? Where do arrows begin? Electrons. Electron arrows. Right. Good. Good. It gets a little trickier when you look at other things that are different. So I shrink that down a little bit. What if I change the substrates? What if I use OH minus here, plus, in this case, I'm going to use CH3 with methyl bromide, and what it's going to give me is H3COH plus Br minus. Okay. Let's do the same analysis as before. Maybe should we do the mechanism first maybe for this one? Maybe that'll help. Let's do the mechanism first for this one. Right? So we always do mechanisms, right? Again, somebody has electrons, somebody wants electrons. In this case, they've even told us, they've showed us the products. So we can look at this and say what bonds were formed and what bonds were broken. So what bond, so if I say bonds formed, what bond was formed? What new bond do we create? A sigma bond, right? Let's talk, see, a sigma bond between carbon and oxygen, right? What bond did we break? We broke the bond between, a sigma bond between C and Br, right? So we need to have a mechanism that shows that. Right? Our mechanism needs to show that. So how would that work here? So the oxygen, right? This oxygen is going to be end up bonded to what? The carbon, right? So I need to show electrons attacking that carbon because that's where the new bond is going to be, right? So let's draw electrons attacking that carbon. And then the two electrons that were in that bond are going back to that bromine. Right? And the two electrons that we use to attack are also right there. We see that? Bonds broken, bonds formed. The mechanism shows how that happens, how the electrons moved. So now let's label them Lewis acid, Lewis base, Bronsted acid, Bronsted bases. Let's think about that now. So this is obviously the base, right? We'll give it another name later, but base is fine for now. It's electron rich, right? What kind of base is it? So if it's a base, it's going to for sure be what? Electron rich, so it first has to be Lewis. What's the definition of a Bronsted base? It's a special type of base. One that grabs protons. Is this base forming a new bond to hydrogen? No. So is it a Bronsted base? No. So you notice how OH minus could be, right? In one case it's a Lewis and a Bronsted. In this case it's just a Lewis. So this is definitely the acid then. We call it that. What kind of acid is it? For sure it's a, is it donating, does it have a weak bond to hydrogen? Polar bond to hydrogen? Nope. So it's not a Bronsted acid then at all. So looking at number 1 on the 2014 quiz one, the question says rank the overall dipole moment from smallest to largest. So what we have here is a good question because this is going to take into account dipole moments, but also we have to think about electronegativity differences too. Right? Who's going to form a bigger dipole? So, and then also I'd read instructions because I tricked you a little bit. I said smallest was actually 1, a small number, and largest dipole was 4. So we have H Cl, Cl, H's, fluorines, H, and then there's an H there, fluorine to fluorine. Okay. So how to analyze this? I just start looking at, okay, what's different and what's the same. So 2 of them have chlorines, right? So if I label these A, B, C, D, so there's some fluorines and some chlorines. So I look at the periodic table and say, what's the difference between fluorine and chlorine? Fluorine's more electronegative, right? So electronegativity is going to matter here for dipoles, right? Dipole is all about electronegativity. So fluorine's more electronegative. So that should give me an idea in my head. Well, fluorine's more electronegative. That shouldn't matter. Maybe I even write that as a note to myself next to the quiz question. F is more electronegative. Right? If you don't write that, can I give you any points for that? I cannot. So things you don't write, I can't give you credit for. Right? You earn points. You'll never see a minus sign on any quiz. Everybody starts out with a 0. I add up points. You earn points. But if you don't put anything, I can't give you any. You can't earn points, right? I can't read your mind. So writing stuff like this, right? F is more electronegative. It's not a bad thing, right? So you wrote that, so you know that, so you knew what to look for. So let's look at our fluorine ones. So this one has 2 fluorines. This one has 4 fluorines. So you might think, oh, 4 fluorines is better than 2. But be careful. Molecules exist in 3 dimensions, right? That's what this wedge and this hatch mean. So if you have 4 fluorines and they're all pulling, right? That's that cheerleader stance. They're all pulling in the same direction. Are you going to actually have a dipole? No, they're all going to cancel each other out, right? So that all 4 fluorines is actually going to be, right? That's actually going to be ranked number 1. That's the smallest dipole. That was a little trick there. But now you go to the other fluorine one that has 2, right? 2 fluorines pulling on your arms while your 2 feet are dangling there. That's going to be a pretty strong dipole, right? And 2 is always better than 1. So I would say the F there is going to be have the largest dipole, right? Because fluorine is the most electronegative. Versus the chlorine, right, which we come back to here. Fluorine is more electronegative than chlorine, so that makes sense comparing these two. I would say, right, this is going to have to be 3, and then 1 chlorine is not as good as 2 chlorines, so on and so forth. So the part of the question, right, is, do you understand that these are in 3-dimensional structures? That's part 1. The other part of the question was, do you understand electronegativity differences and how that will affect these? So another problem here, effectively asking you to understand that all Lewis acids are not Bronsted acids, and all Lewis bases are not Bronsted bases. That's essentially what this problem is going to make you think about again. So what you have here is you have what we call a benzene ring that has 3 pi bonds. They drew in the hydrogens here. There's hydrogens actually on all of these. Quick question, what's the hybridization state of all these carbons? What's the hybridization state of all those carbons? sp2, right? They all have 1 pi bond, right? They're sp2. So the hybrid orbitals for an sp2 hybridized atom are what? A p orbital. And what are the other 3? 3 sp2s. Very good. What's going to happen here, they're showing, okay, they're saying plus Br, a bromine with 6 valence electrons. So what's the charge in the bromine with 6 valence electrons? Is it happy? No. Right? Bromine normally has how many valence electrons? 7. So if you take away electron, the bromine's going to have a positive charge. So it'd be bromine plus. and they're giving you the products. They're saying, okay, here's the product. All these H's are still there. Don't worry about them. I'm going to put bromine there. I'm going to put a plus charge here, and that H is still there. Whoa. I don't know what's going on here, but you can figure it out. I've told you, right? If you already know the products, right? Good, just like in chemistry. If you know the answer, I can explain it. So you guys can do that here, right? Here's a reaction you've never seen before, and won't see till next semester, but you can explain it, right? How are we going to do it? So we're going to do a mechanism. Usually, the easiest thing to do before we do a mechanism is bonds broken and bonds formed. So bonds broken. What bonds did we break? First thing I would always like to do is number your carbons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Should always number your carbons. That'll help us explain this. So which bonds did we break? What bond did we break? Be careful. What kind of bond did we break? We broke a pi bond between which two carbons? Between C1 and C2. Very good. What bond did we form? A sigma bond between C1 and Br. Very good. So we need to draw a mechanism that shows that. So we need to break a pi bond and make a sigma bond. So how are we going to draw the mechanism? So we broke the pi bond between carbon 1 and 2, right? So let's draw those two electrons in, right? And that's where I'm going to start my mechanism, right? That's where I'm going to start my arrow. That's the electron-rich part, right? Because bromine has a plus charge. Is that electron-rich, do you think? So that would be what to you? A Lewis acid. It's not really an acid, but it's an acid. But it's a Lewis acid, right? It's electron deficient. Our broad definition of Lewis acids is what? Electron deficiency. That's pretty broad. That could be a lot of things. And our other partner then must be what? It must be a base, a Lewis base, because it's electron rich then. And which part is electron rich? That pi bond. Why would you pick a pi bond? What is a more reactive bond? A pi bond or a sigma bond? Which one has less orbital overlap? A pi or sigma? So which one's going to be easier to break? Pi. Oh boy. Here we go. Electrons move and they attack that bromine with the plus charge. So who lost electrons in this deal? Which carbon lost electrons? Who lost electrons? C2 did, right? Everybody see that? How these two electrons here, right? Where do these two electrons end up? They ended up in that new sigma bond we formed, right? That's where those two electrons ended up. So who lost electrons in this whole deal? C2 did, right? Everybody see how these electrons are, oh, see you later. Poor C2 now has the plus charge. Because we have an overall plus charge here, we have to balance our charge too. Do you see that? All right, taking a look at number 8 on quiz 1 from 2014. This asks us, why is the alkyne CH bond acidic despite having a strong nonpolar CH sigma bond? All right, so let's draw what I had here. Two arrows. OH minus. So this comes back to asking, so why is this reaction, basically it's asking why does this take place? Right? Everything you know about CH bonds is that they're not reactive, right? They're not polar, right? CH bonds are not polar. So why does this take place? Why does this even happen? So we go back to our rules for reactions. What are our two rules, right? So if a reaction is going to take place, you have one thing or both of these things. What's the first one? You either have reactive starting materials and or stable products. So here's the deal. I just want that little part. So you can do that. Oh my gosh. So here's the deal. So we know, right? I told you in the question, I said, why is the alkyne CH bond acidic despite having a strong nonpolar CH sigma bond? So you know the answer. It has. So if this reaction is going to take place, it must be because this is stable, right? That must be the reason. Go away. Right? That must be the reason. So why is it though? Why is it a stable product? It comes back to, if we draw the mechanism, electrons attack, this bond breaks, those two electrons go there, right? What hybrid orbital is making up that CH sigma bond? For this carbon right here is what hybrid state? It's sp, right? It has two pi bonds. Right? This is an sp hybrid orbital. So it has two pi bonds and two sigma bonds. So its molecular orbitals it has for it, there's two p's and then two SPs. There's something special about the SP orbitals. If I put what do you know about SP orbitals? About their shape. What kind of shape do they have? They're a little rounder, right? They're half S, right? So they're more circular. That means they're closer to what? They're closer to the nucleus. What's in the nucleus? Protons and neutrons. Protons have what charge? Right? Electrons have what charge? So if you can put the negative charge close to the nucleus, the protons, that's going to make you stable, right? First commandment is opposites attract. It's going to lower your energy, right? It's going to make you more stable, right? So the key here is that this lone pair right there is in an sp, right, orbital. That's close to the nucleus. sp2 and sp3, those orbitals are too far away from the nucleus. It makes something that's super unstable. It's just never going to happen. Right? So this is a sapling question. This is around 24 in chapter 2. He's asking you again to classify each of the following as a Lewis acid or Lewis base. So again, definitions. Bases are electron rich. Acids would be electron deficient. Right? And it looks like they didn't do you any favors here by putting in chart. Oh no, that's fine. Yeah, it's okay. So there's a couple tough ones. So there is. They have Na plus. They have beryllium Cl2. They have H minus. They have OF2. And they have SO3. So the first thing I have to do with these, there's a couple ones that you can probably pick out really easy and be done with them. The other ones you're probably going to have to draw out the actual Lewis structures, the expanded structure. So which ones can we just say right away, which one's a Lewis base for sure? H minus, right? Base is what? Electron rich. There's a minus charge. It's electron rich. Right? So that's a Lewis base. Good. Which one's a Lewis acid for sure? Na plus, right? It's electron deficient. Easy. Now these other ones, let's draw them out. And we'll have to probably look where they're at in the periodic table too. So beryllium, so Be, let's see, where's Be at the periodic table? Oh, beryllium. Top left, right? It wants to have two bonds. So it's bonded to chlorine. Beryllium's above magnesium, right? So you probably know magnesium, right? It's also the far left of the periodic table. So is that going to be electron rich or electron deficient, do you think? Usually when we're talking about these, we don't talk about the things bonded to, well, it actually doesn't matter, right? It's going to be what? Electron rich or electron deficient, do you think? Beryllium. So on the far left side of the periodic table. Deficient, right? So it's going to be a Lewis what? Acid. Right? Some people say, well, what about the chlorines? They're electron rich, right? Somebody say that. Hey, the chlorines are electron rich, but wait a second. Yeah, they're electron rich, but a Lewis base is not only electron rich, it actually usually wants to give up those electrons, right? It's reactive. Does chlorine want to give up its electrons? No. So it's not a Lewis base. Right? Chlorine doesn't want to give up. It's a, right? It has 7. It's really super electronegative. Why would it give up its electrons? So don't confuse that with, right? Don't confuse, right? Being a Lewis base means you're reactive, right? You're actually going to be a decent Lewis base, right? Chlorine's not a Lewis base, even though it has lone pairs. Some people say, "Oh, look at all the lone pairs," right? But does chlorine want to? Is chlorine in the business of giving up its lone pairs? No, it's chlorine. It's electronegative. No way. Good. What about this oxygen bonded to fluorines? That's a weird one. Right? Well, what's it going to be? Electron rich or electron deficient, do you think? What do you guys know about fluorines for sure? What are fluorines? Are they electronegative? So fluorine has the same deal, right? It's got a lot of lone pairs. But are those lone pairs actually reactive? Are they? No. So, but here you have poor little oxygen. It's got 2 fluorines on it. Is fluorine electronegative? Yeah. So what do you think fluorine's going to do to the oxygen? Make it electron rich or electron poor? This is actually a weird one. I might disagree with this one. There is still lone pairs here in the oxygen. I don't like this one. They're going to call this a Lewis base. They're saying it's electron rich on the oxygen. I kind of think that's a bad question. Okay. Right? I give you arguments either way. Right? There's still lone pairs here in the oxygen, but if you got 2 fluorines pulling on you, it's pretty Lewis. Lewis acidic, I think. But hey, maybe it reacts like a Lewis base. You'd have to run the experiment. I can argue either way. But they're calling it, which, of course matters, a Lewis base. It's okay to, right? If you, on a test or quiz, and you could explain it either way. You say, well, oxygen has lone pairs, I think it's electron rich, it's Lewis base. You could say, hey, the oxygen's bonded to those fluorines, they're pulling away electron density, I think it's going to be Lewis acidic. Cool. Both answers work. All right, it's my job not to give you a question like that. But if I did, and you explain it that way, that's okay. All right, it's all about the explanation. We want to see your understanding. All right, let's do the last one. So the last one is SO3. What's that going to look like? It's going to look like this. All right, sulfur, of course, can expand its octet, right, because it's lower in the periodic table, so it can have 6 bonds. How many bonds does oxygen want to have? 2. So now in this case, what do you think this is going to be? Is oxygen really prone to giving up its lone pairs usually? Who's more electronegative, oxygen or sulfur? Oxygen's more electronegative, it's higher up in the periodic table, right? So what is this going to be? This poor sulfur is going to be delta plus, electron deficient, so we'll call this one a Lewis acid. And to some extent, this is a knock on this question, right? You can be within one molecule, you can be both electron rich and electron deficient, right? A certain element in one part of your molecule, one element could be a Lewis base, and the other part of the molecule, an element could be more Lewis acidic, right? So really we got to talk about individual elements, not necessarily the whole thing, right? When we talk about bases and acids, we talk about that element or that lone pair, right? Not the whole molecule usually as a whole. It's tougher to do it that way. So this is number 19, chapter 2, sapling. And it's about asking about arrows and also about why, and probably more or less why things would be favored the other way. So I'm just going to draw this one out. So you have sulfuric acid, or the conjugate base, of sulfuric acid, and you have H3O plus. So the first part, let's draw the mechanism, right? So there's electron richness at the O minus, right? That's where electron density is at. We'll draw in some lone pairs here. We'll draw in the lone pairs here, right? That's the most polar bond, right? The oxygen has a plus charge, but where is the electron deficient actually at? Are we going to move electrons towards the oxygen? Or more towards the hydrogen, right? Because the oxygen, even though it has a plus charge, it's not really where it's delta plus. It's really delta plus at the hydrogens. And you could have picked any of those. It doesn't matter which one you pick. Now leave the arrow spot blank for right now, because that's part of the question. And the product here is that. Good. Everybody okay with that? The second part of this question, though, says, what do you put in that box? So here are your options. You have A, which is this. You have B, which goes that way. You have C, which favors the products. And you have D, which is about a 50-50 mix. So the question is, which one? You should be able to eliminate one right away. So this is an acid-base reaction. So it's necessarily an equilibrium reaction. Which of these is not like the others? A. What kind of arrow is A? It's actually a resonance arrow. That's a resonance arrow, so it's not A. Now you got to decide, right, what's more stable, the products or the starting materials? So it's a little tough one, but you got to remember something. What are we making? What is this again? What is this right here? What's the name of that structure? What's the name of that molecule, that structure? What's it called?
Sulfuric acid.
Sulfuric acid, which of course is one of the strong acids. What do you guys know about strong acids? They're reactive. So do they completely dissociate?
Yes.
So is sulfuric acid gonna, if we have sulfuric acid around, what's gonna happen to the equilibrium? Which way are we gonna go? Away from, right, this is gonna react. It's not gonna sit around. Sulfuric acid doesn't sit around, right? So which arrows make the most sense? B do. Now there's another part to this though too, to explain it. What else can this conjugate base of sulfuric acid do that helps stabilize it? Right, so this is definitely a reactive starting material, right? This bond is very polar. These are induction, right? These are pulling away electrons. What can this product do?
Move the electrons around.
You can move the electrons around. What's that called? Resonance. So here I'll just draw it. Right? Even though it has a charge, right? Just because something has a charge doesn't mean it's necessarily bad. Right? One of the things you learn, right? Charges are always bad, right? That's not necessarily the case. If you can spread the charge out because you're a big old fat I minus, or you can do resonance, that's a good thing. So put the negative charge there. Move the electrons. Resonance arrow. Right, we can even move it to this other oxygen too, right? We can spread this negative charge out over 1, 2, 3 oxygens. That's great. That's really good. That makes me really happy and stable. Right, so that's another reason why this reaction takes place, right? Besides knowing the fact that, right, this is sulfuric acid, I know it fully dissociates. Right? Also think about, right, this bond is really reactive because it's being pulled, right, because of the polar bond, because of induction. But also the product you make is stabilized because of resonance as well. If I gave you the pKa's, it'd be easy. Give you the answer, right? Lower the pK, the more acidic, right? So don't forget that too, that basic fact. Right? Yeah. Well, I mean, that's the thing with sapling. Make sure you can look up the pKa's, right? They're in your class notes. I think I've given there. They're definitely in your textbook. You can find the pKa's too.